Welcome to Signals Synapses, the podcast of the Max Planck Institute for Biological Cybernetics in Tübingen, Germany. In this episode, we turn our attention to magnetic resonance imaging, or MRI, and explore how different types of MRI techniques shape the way we see and study the human body. We're joined by Kai Buckenmaier, a group leader here at the MPI. Kai is tackling something that, at first glance, sounds almost impossible: magnetic resonance imaging with very low magnetic fields. I'm really curious to learn about how you can get meaningful magnetic resonance images when the magnetic field is barely there. So now, I'm happy to hand over the mic to Dana Ramadan, who is working with MRI at the opposite end of the spectrum, with extremely high magnetic fields. She and Kai will explore the different approaches and innovations in the field. Dana, take it away.
Thanks for inviting me to co-host this episode. I would like to start with the personal question. So what got you into MRI? I mean, for me, it was more that I am really fascinated about looking into the living human body without having to slice it up. And then it was the MRI that really fascinated me the most because I really didn't understand it in the beginning. So maybe that was made me more curious. So what about you? How did you get into working with MRI?
Yeah, hi Dana and hi Sophia. Many thanks for inviting me. It's really nice to be here. Yeah, that's a good question. So actually, I started quite late with MRI because my PhD I did in superconductivity, so a different field.
So you're a physicist, actually?
I'm a physicist, yes, exactly. And during that time, I worked with superconducting quantum interference devices, so-called SQUIDs. You might hear this word more often during this podcast. And those are really fantastic sensors because they can measure the tiniest magnetic fields. They are the most sensitive magnetic field sensors on Earth. So they can, for example, detect also the brain activity directly. So this was my PhD thesis, and it was quite, even though we did experiments, it was far away from application. So I thought, maybe which goes slightly more in the direction of applications would be better. And so I did a postdoc in Berkeley with John Clark, and he was doing ultra-low field MRI. And low fields means also low signal. And the nice thing what John Clark did, he used SQUIDs as magnetic field detectors and was doing MRI with those SQUIDs. So it was sort of a perfect match. I learned there the ultra-low field techniques, and that brought me after my postdoc to Tübingen, and there we started this ultra-low field project here in Tübingen.
Yeah, I think we'll get to the fields and what this all means with the ultra-low field, ultra-high field, what we actually mean with all of this. But first off, I think we should kind of tell our listeners what MRI actually is. I think all of them have an idea of what it is. I mean, it's a tight tube that is uncomfortable and loud. And maybe, they should know that these sounds actually do have a meaning. And maybe you can explain to our listeners slowly, briefly, what MRI is.
Yeah, that's a good question. I mean, MRI machines, they are fantastic machines. They are capable of making 3D images of the human body in incredible resolution, like in sub-millimeter resolution. And by doing so, they are capable of doing diagnostics of a huge variety of different diseases, which is really fantastic. But as you mentioned, they also have some drawbacks. You have to slip into this tube. They are loud. And it takes quite a long time to make an image. It's not like X-ray where the image is done within a few seconds. In MRI, it takes quite a long time to get an image, especially if you want to have a high-resolution image of your body. That takes quite some time. And you must know that. You are a high-field expert, right?
Yes, I know. I know that it's slow, and this is the main drawback. But we get different contrasts. And this is nice because you can look at the image and you can really see the tissue, right? Which you cannot with X-ray, where you just shine through and maybe also damage the DNA.
So you're a physicist. I don't want to do a physics podcast with you, but maybe we can dive a little bit into the principles of what is actually going on there in these noisy machines that you described.
Yes, sure. So in principle, MRI is a quite insensitive method because what we are measuring is the polarization of or the magnetization of spins. And now it is...
So what's a spin there? Sorry to interrupt you right there.
Yeah, what is a spin? That's difficult to explain. And so there's a simple analogon which is not quite correct. So in principle, a spin can be seen, not quite correctly, as a bar magnet, as a really tiny bar magnet with the size of a small atom nucleus. Yes, and now it is that we are only measuring the those spins of water, so of protons or hydrogen, and for conventional MRI experiments.
Yeah, and we do that for two reasons. First reason is that we have a lot of it in the human body, and the second reason is a bit more physics-oriented, right? It has something to do with the gyromagnetic ratio.
Yes, so they have the highest gyromagnetic ratio. It's just a property of the spins, this gyromagnetic ratio, and protons have the highest gyromagnetic ratio, and that means they also have the highest magnetization, so they produce the highest MR signal. And you already said it, we have a lot of them inside the body, and we need a lot of them because what's happening is that those spins, if we put them in a magnetic field, they will align with a magnetic field, but then there are thermal fluctuations and they will whirl the spins around, and meaning that only a few of the spins are counting for the magnetization. In other words, in easy words, it's like that if you take a bottle of water, 1 liter of water, and what counts for the MR signal is only 1 drop of this bottle of water. So there's not a lot of signal left, and that's why we need those many spins.
Okay. It seems like this technique we're using is super inefficient, right? We're using 1 drop of this whole liter, and we could make it better. We could use maybe 2 or 3 drops, right? And this is what we're trying to do if we're not using the normal magnetic fields that are used at a clinic, but we go to higher fields.
So that's what you do?
Yes, this is what I would do. But you do something else. You go to lower fields, you go the opposite direction. And you have a different technique of how to enhance the signal there. How do you do it?
Yes, Dana, you're right. What we are doing in the ultra-low field regime or low field regime, you mentioned it already, there's not much signal left. So we have to do tricks. And there are chemical and physical tricks how we can enhance the signal. What we are doing is so-called hyperpolarization. And with hyperpolarization, what we can do is we can nearly hyperpolarize the whole bottle of water. So let's say 80% of the water, of this 1 liter of water, means then is aligned with the magnetic field, and also counts for your MR signal.
So if I'm getting this right, in hyperpolarization, what you're doing is you align a lot of those protons and hydrogen in the same direction, so that in the end you measure signals from more of these spinning protons, right?
Yes, exactly. And for that, we need a system with a really high spin order, because this is what we need. If all spins are aligned, this is something which is ordered, and we need order. And so we need a system which has a lot of order. And one technique which we are using is so-called parahydrogen-induced polarization. And parahydrogen has some physical properties which are really nice. Parahydrogen consists of two nuclei, two protons, and the spins of those protons are showing up and down. So in principle, parahydrogen has no MR signal, but it has a lot of order.
Because up and down cancel each other?
Yes, exactly. Yeah. And what we need then is a catalyst and a ligand. As example, we can use pyruvate as a ligand, which is also really important for metabolism inside the body, and it's non-toxic. And what we can do then is we can transport this spin order from parahydrogen via the catalyst to the ligand. And what we also need to do is to break the symmetry. This up-down symmetry we are breaking off to an up-up symmetry. And by doing so, we get this pyruvate hyperpolarized, and we are getting quite a lot of polarization level there.
So these hyperpolarized contrast agents, what I understand, they would be field independent, right?
Yes, exactly. So the magnetization is then independent of the magnetic field strength of your MRI system. And that gives you the possibility to go to lower fields. So you don't need a 1 Tesla magnet to measure those hyperpolarized contrast agents. You can also go to the low field regime, so let's say 50 millitesla, or to the ultra low field regime, which is below 10 millitesla, or even Earth field, or below the Earth field. It doesn't matter.
But you then also, so if you're doing experiments at ultra low field, you always need to have a very good shielding of the magnetic field, right?
You need a magnetic shielding as soon as you get below the Earth magnetic field. This is correct, yeah. So one trend is to only go to the low field regime, let's say 50 millitesla. This is a range where you can really build cheap machines. You don't need those huge superconducting magnets anymore, which you need for high field MRI. This is one advantage. And another advantage is if you go to lower field strengths, then those systems get also more silence.
So we've mentioned now a few times that it's really loud in conventional MRI machines. Now you say your new devices are not that loud. I really want to understand, where does this noise actually come from, and why are your machines not that loud?
Okay. Yeah, in principle, what those high-field MRI machines are, they are like big loudspeakers. What a loudspeaker contains is a big magnet, permanent magnet, which is in our case this superconducting magnet around our MRI machine, creating the strong static magnetic field. And what you also need are changing magnetic fields. Usually in a loudspeaker, you have just an electromagnet, which you switch off and on, and you put a membrane on this electromagnet, and that swings, and that creates sound. This we don't have in MRI, but what we have are the gradient coils, which are also switched on and off quite fastly. And yeah, if you switch magnetic fields on and off in a strong static magnetic field, that creates sound. And there's actually a lot of effort to make those machines more silent, but it's difficult because those gradient coils, they must be embedded in, they should be stable. So they are embedded in some resin. It's difficult. You cannot really make them silent. But if you go to lower field strengths, then your permanent magnet around your MRI system, it's much, it's only 50 millitesla compared to 1 Tesla. And that means the loudspeaker is much less powerful and creates much less sound.
Okay, but then to put it into context, we need these gradients to localize where our spins are in the human body, for example. So to know where the signal is coming from. And this is why we need the gradients at the high fields that we use in the clinics. But then why would you go to lower fields? What other benefits do we have at lower fields?
Okay, so we mentioned it already. The systems are more silent, but actually there are also other advantages. Example given, what's usually really dangerous in high-field MRI is if you measure like in the vicinity of metals. So needless to speak of ferromagnetic metals, they are like strongly attracted to the magnetic field.
Yeah, they're not even allowed into the magnet, right?
Exactly, that's just dangerous. But also non-ferromagnetic metals can be dangerous because they disturb the RF fields, which we also need. So we need 3 ingredients. We need a B0 field
So the big constant magnetic field?
Yes, exactly, for creating some alignment of the spins. Then we need gradient coils, as you already explained, for getting spatial resolution, but we also need radio frequency fields for exciting the spins. And those radio frequency fields, they lay in the 100 megahertz range for high field, for those machines in the clinic for high field MRI. And those RF fields, they are disturbed by the presence of metals, and they can create hotspots. So that can also be dangerous, especially if you imagine you have some metal inside the brain, a plate or whatever, and then you create a hotspot inside the brain. That's quite dangerous. So, but actually this is a so-called susceptibility effect, meaning all of that is much less dangerous or present in the low field range. So, meaning imaging in the vicinity of metals might be possible, which would like open a new playground, for example, given surgeries or whatever you can imagine.
Mm-hmm. What about the resolution? I mean, we go to higher fields because we know the resolution gets better. And with lower fields, we know the resolution actually gets worse. So how do you compensate for that?
Yes, you are quite right. So in principle, our aim is not to compete with high-field MRI systems. I mean, there are a lot of tricks for getting good resolution images in the low-field regime as well. I mean, you can use some machine learning algorithms and use like high-field MRI data as training data. So you can enhance the resolution, but we will never be as fast or as good in resolution as in high-field MRI. I think this is also not the goal for this community. So, I mean, an obvious goal for the community is to get MRI to less developed regions. One aim, but also another aim is just to find new methods. So what we are doing here is method development. And what is also different to high-field MRI is, example given, the contrast. And if you want to detect different diseases, it's not all about resolution. I mean, resolution, of course, helps always. but it's also a matter of contrast. And there are some things where you don't get contrast in high-field MRI.
So if I got this right, in the clinical practice, people would just inject hyperpolarized pyruvate into the patient, and then they see what?
Yeah, actually, what we usually see in those experiments is the so-called Warburg effect. And especially in tumors, I mean, I'm not an expert in this, I'm a physicist, so this are doing my colleagues more or less. But what they see is then the metabolism, and especially in tumors, this pyruvate is like converted in, example given, lactate and other substances. And so what you can see with this experiment, with this kind of experiment, is you can see where the tumor is also active. Like you not only have an image where the tumor is, but you also see where the tumor is active, example given. And you also might be capable of classifying the tumor. You see how aggressive it is. So yeah, I mean, those are quite relevant experiments, and they are on the brink to clinical diagnostics at the moment. So they will come in the next few years.
But do you actually use them in humans as well?
Yes, they started to do human subject experiments with pyruvate, with hyperpolarized pyruvate. Yeah, there are a lot of studies out now, like over 100 studies.
Mm-hmm. But this means you only see the hyperpolarized bolus you inject.
Yes, with this technique, this is correct, yeah. But there are also other techniques which are not in this stage to get to clinical diagnostics at the moment, but let's say in the methods development state. Example given, Overhaar is a dynamic nuclear polarization. And with this method, you are capable of hyperpolarizing your sample itself rather than a bolus which you inject. Overhaar DNP is a really nice technique. You can do this also in vivo. And actually, this is a research branch which we do at the moment here at the MPI in Tübingen with our ultra-low field setup.
What do you need for that? What's your cookbook for an Overhaar or DNP? How do you do that?
Yes, so in principle, what we need is, of course, a source for spin order, like before. Before, the parahydrogen was the source for spin order. Now we have a different source. We will take the electrons. Actually, we talked before about the gyromagnetic ratio, right? And protons have a quite high gyromagnetic ratio, but actually...
Can you just repeat real quickly what that was?
The gyromagnetic ratio, that was a property of the spins. In principle, the MR signal is proportional to the gyromagnetic ratio of our spin system.
So you want a high gyromagnetic ratio?
Yes, in principle, yes. So protons have for nuclei the highest gyromagnetic ratio. That's why we usually use them as for imaging, also because we have a lot of protons. But actually, electrons have a much, much higher gyromagnetic ratio. It's like 660 times higher than this of protons, meaning that you have also a much higher polarization of electrons. And now with Overhaar MRI, what we do is we couple the spin order of the electrons to the example given protons. And by doing so, we can enhance the signal by easily by a factor of 100. So it's not like before where we really hyperpolarized where the whole sample was polarized. So where we have enhancement factors which are in the order of 1 million. Now we have only small enhancement factors in the order of 100. But still, this is sufficient to do MRI at ultra-low fields. And so what we need is this source of free electrons. And actually, those free electrons, we provide them by injecting free radicals into the animal.
Mm-hmm. Free radicals.
That doesn't sound healthy.
No, that doesn't sound good.
Exactly, that's correct. It's not really healthy. But actually, what you do in high-field MRI as well is you are injecting gadolinium, which is also not healthy as contrast agent, right, Dana?
So that's actually what's being done in the clinics?
Yes, that's done in the clinics. And why can you do this? Because you use a carrier system for your gadolinium. You pack this gadolinium in a macromolecule, which makes it safe for the human body. And we can do similar things with free radicals. We can try to embed them in like stable structures. And actually, this is one of the bottlenecks of this technique, to find really suitable carrier systems for those free radicals, because now we want to interact those radicals with the surrounding, but not too much, right? So we want like water molecules. We want to interact the water molecules with the free radicals, so we can like transfer the polarization from the electrons to the water molecules. But on the other hand, we don't want the radicals to react with biomolecules, which would mean that those radicals are toxic. I mean,
and which carriers do you then use?
Yeah, so we tested a lot of different carrier systems like liposomes or dendrimers. But actually what we found out is that, example given, human serum albumin is a good carrier system, which is quite stable also inside the body. And another system which we are testing soon is a so-called tobacco mosaic virus. Yeah, virus sounds also dangerous, but actually it's only dangerous for tobacco plants. So not sure if smokers should use this contrast agents. But for humans, actually, it's not really dangerous. And that's quite a nice system because this tobacco mosaic virus, it's like a nanorod. And what we do is we bring the free radicals inside this nanorod. And water molecules are capable of penetrating this nanorod, but biomolecules are not capable of penetrating the nanorods. Yes, exactly. They are too big. Yeah. And I mean, that's a nice system. Then we can like hyperpolarize the water molecules inside the body, but still it's safe. Yeah. So this is one system we are going to test soon. Yeah.
Okay, so that means, to sum it all up, we have hyperpolarized pyruvate, which we can use at any given field strength, which is also very beneficial for ultra-low field because this hyperpolarization happens at this ultra-low field. But then we also have, on the other side, Overhauser DNP, which cannot be used at any given field strength, only at ultra-low field. And for this, you need a carrier, and this is still not feasible for humans, but the pyruvate, on the other hand, is also used for human subjects. Okay, I mean, this is all fun and all, but what good does it actually do humanity? So does it change bioimaging as we know it today? Can it replace MRI at some point?
Yeah, I mean, I told it already, and I'm always really careful with replacing high-field MRI. This is, I think, not feasible and not possible. What we are trying to do is to create additional methods for MRI. So we want to expand the portfolio of MRI. I mean, we already have a really great portfolio of MRI. It's used for diagnostics. Also, you can use it for other things, like you can check if your corn is ready for being harvested or whatever. There are a lot of applications. And with our methods development experiments, we just try to expand this portfolio. So we don't want to replace high-field MRI. I think it's necessary to have this always, but maybe we can find some contrast for specific diseases which you cannot see in high-field MRI, but maybe with those low-field MRI systems or those ultra-low-field MRI systems.
That wraps up our conversation for today. A big thank you to Kai Buckenmaier for sharing his experience and perspective on MRI technology, and of course to Dana Ramadan for leading such an insightful conversation. If you enjoyed listening, don't forget to subscribe, rate the podcast, and share it with your friends or colleagues who might be just as curious as you are. You'll find more information and helpful links in the show notes. Thanks for tuning in, and as always, stay curious and keep listening.